designed systems can be installed in the form of software in the machines and computers, and that actually smartphones, and that such kind of systems with these algorithms are very useful in rural areas where we can identify a disease at the initial level by using such kind of systems. And similarly, in urban areas or in hospitals, these doctors also can use such kind of systems where these systems can help them in their diagnosis process, and where these systems can improve their efficiency in the diagnosis of the various diseases, and in this case it is brain diseases. So with this background, let us start this talk. So this is the overview of this talk. First we will see introduction of machine learning, and after that we will see application of machine learning for EEG signal analysis, and then empirical mode decomposition based features for analysis of normal and seizure EEG signals, then classification of seizure and non-seizure EEG signals, and the detection of epileptic seizures. And after that, we'll see time frequency image-based features for classification of sleep stages, and then multi-wavelength decomposition-based features for human emotion classification. And in the end, conclusion will be provided. So first, let us try to understand machine learning. And machine learning is actually is very simple term these days, very common term. Everybody talks about machine learning, whatever research area, but you can find people are trying to use machine learning because everywhere we are interested in automated design of automated system. We want to do things in automated manner. So this machine learning actually inspired from like real life, in real life also we learn from the experience by like from the training, and then we perform or we perform the testing. So similarly, like a newborn baby, and he or she learns from the mother. Mother is a first teacher, and after some time, this learn after learning completes, and then he or she can perform activity and see many activities without asking mother. He or she does. So, for example, mother introduces whose uncle, various whose family members in the family, and after some time, automatically these babies or newborn they try to learn automatically. They try to understand, and they don't ask mother who is uncle or who is other family members. So in that way, the same kind of actually behavior, same kind of system that we want to implement with the help of these computers and machines. That is actually the concept of machine learning. So machine learning is an umbrella term for a set of tools and techniques which can help computers, machines to learn and adapt their own. And according to Herbert Simon, this learning is any process by which system improves performance from the experience. So if you see any applications of machine learning, there is actually it is very difficult to find any area of science and technology where machine learnings are not applied. So, but in broad manners, we can see it's like automated health diagnostic systems, product recommendations, image recognition, sentiment analysis, fraud detection in banking domain, language translation, medical diagnosis, uh, email spamming, malware filtering, self-driving car. These days, driverless cars are coming. Machine learning is very helpful to drive the car, and where we have to navigate car, take the directions, and this features are very useful. Product recommendation, traffic prediction, automated signaling based on the machine learning, image recognition, speech recognition. You can see in the smartphones based on the speech or based on the thumb impression. Actually, you can enter in the device. They will understand. They will understand that you are the right user. There are two important parts in machine learning. One is training and other one is testing. So the observations in the training set from the experience that algorithm uses to learn, and the testing is actually a set of observations which are used to evaluate the performance of the model based on some performance metric. So this training and testing, and based on this, there are majorly actually three types of machine learning based on the nature of the data: the supervised, unsupervised, and reinforcement learning. So supervised, we know what is the actual outcome. what is the classes corresponding to which category, which kind of data. And unsupervised, actually, we don't know what is the outcome, what is the class of that particular data. And reinforcement learning, that is based on trial and error method. So we based on the feedback, and based on the update, we try to learn in automatic manner. So based on these actually methods, there are different classifiers like K nearest neighbor KNN, artificial neural network ANN, support vector machine SVM, naive Bayes, decision tree, logistic regression. And here you can see this one nice example of this machine learning based classifier. So we have two classes, class A and class B, and these two set of features X and Y. So this is X direction, this and this is Y direction. So these two features are two-dimensional features, and here actually, if you see by putting this boundary line, you are able to separate these two classes. So sometimes in real domain, in actual domain, we are not able to separate the data based on the features, but we project them in the high dimensional space, where actually nicely we can separate them. These two classes can be separated. So in that way, nicely separation can be carried out in high dimensional space. And this is actually one of the very interesting in these days, that is smart healthcare monitoring system. So where actually machine learning plays important role, and the signal processing also very useful. So here you can see this human body, it is full with the signals like electrocardiogram, ECG signal, electroencephalogram, EG signals, blood pressure, blood sugar, oxygen saturation, heart rate, position, electromyogram, respiratory rate, cholesterol level. And here actually these so physiological signals now, this each signal has a lot of information. So we use them, these signals, and we extract the features, and then these features, we also have some EMR data, electronic medical records, and based on that, actually, we can do the detection, early detection of the disease, whether this, for example, heart disease is present or not. So similarly, it can be done with brain disease or other kind of diseases based on these physiological signals. So that actually we can do evaluation the features, and based feature when is going in the abnormal range, then actual alarm is on, and that can, so this person will be informed, even hospital will be informed that this person is going to have a heart attack or going to have a particular disease, so that in the initial level itself actually we can go for the treatment. So that is such kind of actually this process where signal processing machine learning based techniques actually design this system that is known as smart healthcare monitoring system. So this is actually one of the very interesting area of research, and where we have data manager, hospital, patient, all are actually connected with to each other, and that is one of the important application of telemedicine, where nicely disease can be diagnosed at the initial level, and required treatment can be taken in that within that time, so that it is good for the actually to disease for the like having good health. So now we will actually use this applications of machine learning for EEG signal analysis. So this human brain, this talk is focused on EEG signals. So human brain is a highly complicated and nonlinear system, and this electroencephalogram, which we also call EEG signal, is measure electrical activity which is generated by the neurons in the brain. So EEG signal actually is a very useful tool in order to investigate different physiological and pathological states of the human brain. And quantitative analysis of EEG signal is a challenging task, because these signals are complex, complicated, and irregular nature. And non-state signals. Non-state signal means like we use mathematical models to represent the signal. If any of the parameter is changing with time, then we call them non-stationary signal. So this EEG signal is actually highly non-stationary signal, and it has been shown even if you take a very less number of samples, for example 20 samples, then also this EEG signals models whatever we use to represent them, and they change with time. They found non-stationary. So the visual scanning of EEG signal is very time consuming, and like generally doctors perform visual scanning. When you go to hospital, they will record your EEG signal and they perform visual scanning. That is very time consuming, and sometimes like for example, person may have repeated seizures. So like in a day he is getting 2 seizures. So every time monitoring is very difficult. So such kind of methods may be inaccurate also, because when you print these signals on the paper, then variations may not be clear. So it is very complicated and it is subject to judgment and suffers from human error. So like different neurologists can have different opinion on a given signal, and it is also performed by the trained professionals. So due to these reasons, there is actually a lot of motivation in the literature for developing automated systems, expert system, intelligent systems based on the signal processing and machine learning techniques for identification of EEG signal in automated manner. So the actually first part of this talk is analysis and classification and detection of epileptic seizures. And epileptic seizures, which we also call epilepsy, these are the outcome of the transient and unexpected electrical disturbance of the brain. So brain is all neurons, they synchronize together and they generate very high electrical activity. And this brain actually is the master of the body, and due to that, if brain is disturbed, and then actually everything is disturbed in the body. So this disease affects around 2% population of the world. So we have proposed area parameters for analysis of normal and epileptic seizure EEG signals, and bandwidth parameters for classification of seizure and non-seizure EEG signals, and the statistics area for the automated detection of epileptic seizure. So normal means they never had epilepsy disease, and epileptic seizure means at present they have epilepsy disease, and non-seizure includes seizure free and normal. So like seizure free means earlier the person was having seizures, but now treatment has been done, now he is seizure free. So in that way, these three methodology will be explained in detail. So, in this actually work, we have proposed this empirical mode decomposition based features. And before empirical mode decomposition, what is the motivation for using empirical mode decomposition in this work? Let us start from the basics of this basic analysis technique, that is Fourier transform. So Fourier transform, actually what we do, we represent signal in terms of sinusoidal functions. Sinusoidal functions, they are periodic, and they extend from minus infinity to plus infinity. So time resolution and this time localization of these basis functions, that is actually proportional to 1 upon spread. As these signals actually have infinite spread, so due to that time localization and time resolution, that becomes actually 0. So the sinusoidal functions, they are not actually suitable to represent the non-steady signal. So in order to analyze non-steady signal with the help of sinusoidal functions, a short time Fourier transform STFT or windowed Fourier transform was proposed. So in that actually method, what we do, we divide the signal into different segments, and each segment we assume that signal is stationary. And then we apply Fourier transform of each segment. The arrangement of this Fourier transform gives us short time Fourier transform STFT. In STFT, this actually whatever window size we use or window type, that is fixed for entire analysis. So we don't know for the given data which window is suitable, and what should be the size of the window, and different frequency components present in the data requires the use of different size of the window. That flexibility is not available in short time Fourier transform. So then the STFT, actually this wavelet was proposed. In wavelet, we use scale factor, and according to different scales, we can use actually different window functions. So low scale is suitable for high frequency components, and which gives you good time resolution, and large scale is suitable for low frequency component, which gives you poor time resolution. So in that way, actually, we, with the help of different skills, we have actually multi-resolution property of the wavelet for analysis of the non-stationary signals. And here, actually, a good thing is that this wavelet-based method that can be implemented with the help of filter bank, and this filter bank that actually is easy to implement. But even filter bank also, when you use this discrete wavelet transform in the form of filter bank, then there is no thumb rule which will suggest what should be the number of labels for the filter bank, how many labels or how many subbands or how many decomposition labels are required in that filter bank, and which mother wavelet is suitable. So due to these reasons, there is actually in 1998 this empirical mode decomposition was proposed in the literature, where we don't need to design basis functions from our side. Like in case of Fourier transform, we design sinusoidal functions from our side. In case of wavelet transform, we design wavelet from our side. Here we don't need to design basis functions from our side. On the other hand, these basis functions, they are obtained from the signal itself. So we call them intrinsic mode functions, IMFs. So for a given signal, EEG signal, we obtain intrinsic mode functions using this EMD method. And then once you have IMFs, then we obtain analytic signal representation of these IMFs using Hilbert transform. Then area feature, which is based on the modified center tendency measure. And then we apply Kruskal-Weiss statistical test to actually show the discrimination between normal and seizure EEG signals. And in second methodology, we actually determine amplitude modulation and frequency modulation bandwidth features from this analytic intrinsic mode functions. And then these features, these bandwidth features actually, they are given as input to least square support vector machine classifier, which automatically classifies seizure and non-seizure EEG signals. In the third methodology, we actually determine instantaneous area from the IMF, and then actually together with decision rules that actually gives you epileptic seizure detection. So these three methodology we will see in the detail, and the first part actually, that is now let us see some results. So for this study purpose, we have used this publicly available database which was provided by the University of Bonn, Germany, and this data set includes 5 subsets: Z, O, N, F, and S. And subset Z includes eyes open health EEG signals from eyes open healthy conditions, and subset O includes EEG signals recorded from the eyes closed condition from the healthy subjects, and subsets N and F, they actually include EEG signals recorded from seizure free subjects, and subset S includes EEG signal from seizure subjects. So in this way, all 5 subsets, they have actually 100 EEG, 100 into 5 times, so 500 EEG signals, and each signal's duration is 23.6 seconds. So the sampling rate of the EEG signal in this data set is 173.61 Hertz, and these signals have been recorded with the 128 channel amplifier system using common reference. And this EMT method that is actually suitable for nonlinear non-state signal processing. And we have seen this is adaptive method or data dependent method, does not require design of basis functions. It doesn't require assumptions of the condition of stationarity. And EMD method actually can decompose this complicated signal or wideband signal into set of simple signals, narrowband intrinsic mode functions, IMFs. And these IMFs can be modeled using amplitude and frequency modulated signal model. So sometimes actually we call it a generalization of the Fourier representation. So Fourier representation, we represent signal in terms of sinusoidal functions whose parameters are constant, amplitude and frequency. But here in AMFM model, in this IMFs, and actually we allow the amplitude and frequency parameters of the sinusoidal functions to vary with time, and which actually provides amplitude and frequency modulated signal model. So that is actually more general model than the Fourier, and is highly suitable for non-stationary signal analysis. So each IMF satisfies 2 basic conditions. The number of extrema and the number of zero crossings must be the same or differ at most by 1. So this actually condition ensure that whatever IMF we have obtained from the data, that is actually it is like sine cosine function. And the second condition, the mean value of the envelopes, which is defined by the local maxima and local minima, is 0. So this condition ensures that whatever IMF we obtain, that is symmetric in nature. So when we satisfy these two conditions, this actually means that this IMFs whatever we have obtained, they are actually symmetric in nature. They have sinusoidal kind of behavior. So these all actually IMFs or basis functions, they are obtained by this residual concepts. So there is a simple algorithm. Based on that, we derive the first IMF. So first IMF is subtracted from the signal, then we determine residual. The residual is used as a signal, then we determine another IMF, IMF2. Then for third IMF, we determine new residual, which is obtained by the subtracting these two IMFs from the signal. So in that way, actually we continue the process, and in the end we have such kind of signal which doesn't actually provide you any further IMFs, that we call residual. So in the end of the decomposition, signal xt, it can be represented as a sum of IMFs plus residual. So that actually we will see one example. So here you can see this epileptic seizure EEG signal, and which actually have large amplitude and spikes in the data. And now when you apply this EMD method on this data, this seizure EEG signal, then you have various IMFs and residual. So first IMF represent the highest frequency component present in the signal, which is actually known as detail, and the last IMF represent the lowest frequency component present in the data. So this first IMF is also corresponding to the lowest scale present in the data, and the eighth IMF also represent the highest scale present in the data. So in that way, these IMFs actually they are arranged from high frequency to low frequency, or low scale to high scale. So that actually similar kind of wavelet decomposition, we can have analysis of the signal with the different possible scales. That is also one kind of multi-resolution analysis. So here actually we have used analytic signal representation of IMFs. So this proposed method is based on the analytic signal representation of IMFs. So analytic signal ZT of the signal CT can be defined by this expression. So CT is the IMF plus J times C cap T is a Hilbert transform. So which gives you the analytic signal, that is AT e to power J phi t. So AT is the time varying amplitude and phi t is time varying phase. So this analytic signal representation of mth IMF can be given by the equation 2, and this analytic signal representation of IMF actually satisfies the following two conditions. The condition 1 says that plot has directional rotation, and the second condition, the rotation in the plot has unique center. So these two properties actually very important, and they are very useful to define the feature that we will see. So this is one example here. This is the analytic signal representation of EEG signal, and these are the analytic signal representatives of IMF. So in case of EEG signal, we can see this analytic signal representation has multiple centers. So it doesn't have actually any specific geometry. So it's difficult to actually define the area parameter here. On the other hand, if you see analytic signal representation of the IMFs, then it has nice circular structure and it has unique 0,0 edge center. So nicely you can define actually area parameter for the circular structure, which is actually shown by these IMFs analytic signal representation. So now how to determine this area in automated manner? So for that actually we have proposed modified center tendency measure, and by using that we can determine the radius, and from the radius we can compute the area. So if n is the total number of points and r is the radius of the central area, then modified CTM is given by the equation 3. So based on this actually this CTM, this delta D and expression 3, this one if this particular point is actually is falling in case. Otherwise, so in that CTM actually counts the number of points which are falling inside the radius, and for example, suppose if your CTM is 90%, this means 95% points are inside the radius out of that 100% points, out of that number of points. So in this actually work, we have used 95% CTM to determine the radius, and once you know that radius, from that we have computed the area.
How can she change after submitting the marks and that too signed by all other
And
persons?
this actually method is based on the
Ah,
area that also we have actually extended
38, 21
instantaneous
to
area.
38.
So this instantaneous area is measured from the trace of the window dynamic IMF. So like similarly short time Fourier transform, we segment data into different segments, then we compute the Fourier transform. Similarly here for different segment we compute the area, then we interpolate them. So it gives you instantaneous area. So instantaneous area at any point is computed by using a moving window method, and the chosen size of each moving window is 3840 samples, and this window size is uniform for all EG signals. And instantaneous area of mth IMF is defined by equation 4. And then actually third part of this analysis classification of each signal is based on the amplitude modulation and frequency modulation bandwidths of analytic IMFs. So generally whenever we talk about the bandwidth, we generally assume that this is actually spread of the signal in frequency domain. Like we take the Fourier transform and we determine the spread, and based on that actually we determine the bandwidth. But this Cohen and Lee 1990, they come up with a different definition of the bandwidth, which depends on the amplitude modulation and frequency modulation. So this bandwidth actually can be defined in terms of time varying amplitude and time varying frequency. In other words, amplitude modulation and frequency modulation. So in order to have such kind of actually bandwidth due to AM and bandwidth due to FM, we need to have AM FM signal, amplitude modulated and frequency modulated signal. So that actually how to get that kind of signal, that is not easy, because in real life most of the signals are that we see, they are multi-component AM FM signal, and this EMD method gives us such a platform where nicely actually you can decompose this multi-component AM FM signal in terms of mono-component AM FM signal, and this equation 5 can be applied there. So you can have bandwidth due to amplitude modulation and bandwidth due to frequency modulation. Now we will see some results. So let us see some results on analysis of normal and seizure EG signals. So subset Z from the normal class and subset S from the seizure class. And this method can detect patients with epilepsy using EG signals from normal people. And EMD based decomposition makes actually possible to cover more than 95% of data points which lie within the circle due to having circular form of analytic IMFs. And this area parameter have been estimated for both the classes normal and seizure based on the analytic signal representation of IMFs of various window sizes, which are 500 samples, 1000 samples, 2000 samples, and 4000 samples. One of the important part of this diagnosis in medical diagnosis based on the physiological signals is the selection of the length. And if your method actually works on the smallest length of the data or less amount of data, then your method, whatever you propose, that it requires low computational complexity, so it is more suitable for real-time implementation. And on the other hand, this method also actually can be used by for the recording. You need to have less recording of the data, which is actually good for the patient. Patient will be more comfort more. So due to these reasons, we want that our proposed method should work with less amount of data. So we want to have how much less data is actually can be recorded for the implementation of the method. So this is very important actually result. Here in this figure is CTM in terms of percentage is varying with respect to radius. So like normal class, you can see the CTM for it becomes nearly 100% around 300 radius. On the other hand, for the seizure, requirement of radius is very high, and that in order to have 100% CTM. For example, like 1200 or more than 1100 is required to have 100% CTM. So this due to actually here, because the seizure case, you have more variability as compared to the normal case. So that's like due to that, CTM is requirement, 100% CTM requires more radius, and as a result, more area is also required. So this motivates us to associate area with the seizure identification, because in case of normal case it is less, and in case of seizure case it is higher. Now we will see some results, and based on the Kuskova statistical test for the window length when it is 4,000 samples, and for the different IMFs, IMF1, IMF2, IMF3, IMF4, and here you can see this probability value that is actually is coming out to be zero. So probability value, if it is less than 0.05 or 5%, then we call it is statistically significant difference. So for this case, for this window size, 4,000 samples, these 4 IMFs, they provide statistically significant difference. And similarly, when you see the window size of 2048 samples, in that case, that also in this case also this area parameter is actually is providing better discrimination and statistically significant difference between seizure and normal EEG signals. So in this case also probability value is 0. Same thing is observed for window length of 2000 samples. In this case also probability value is actually coming out to be 0. So this normal and seizure classes of EEG signals can be discriminated in a statistically significant manner. And for window length of 1000 samples also, nicely these two classes can be separated with good statistically significant level, which is actually proved with the probability values coming out to be 0. And for 500 samples also, we can have statistically significant difference between seizure and normal EEG signals for the first four IMFs. And this SAMP actually, these results also can be seen in the form of table. And here you can see for normal and seizure subjects, window size 500, 1000, 2000, 4000 samples, and this minimum, maximum, and median value of area parameter can be seen in this table. And from this table, it is clear that for seizure case, this area parameter has higher value as compared to the normal case. So there are actually various methods in the literature for analysis of normal and seizure EEG signals. So like Nigam et al. 2004, Srinivas et al. 2005, Kanatar et al. 2005, Polat in 2006, Subhas 2007, and they use various signal processing machine learning techniques. And they got various classification accuracy that you can see the right, this last column of this table. And our proposed method actually, which is based on the area parameter from the analytic IMFs, and which gives 100% discrimination accuracy. And it should be noted that actually the other methods which we have compared, most of the existing methods in the literature, they use actually analysis part, analysis and classification parts, and the signal machine learning techniques are required to design the classification system. But our method, analysis part itself is sufficient to provide 100% classification accuracy. There is no need of machine learning method. Based on a simple threshold, we can actually classify both the classes. We can discriminate both the classes based on simple threshold. So that is actually that's important aspect of this proposed method. And the selection of the spoon depends on the type of food. If you want to have noodles, then we use fork, because food is discontinuous, so spoon is also discontinuous. Similarly, here also actually the analysis technique depends on the type of signal which we are analyzing. So here, luckily, we got such kind of signal analysis technique which are highly suitable for the analysis of the data, which actually which is nicely analyzed, and so it gives you better discrimination. And you don't need to classify, you don't need classifier in order to separate these two classes. That we have proposed a method for classification of seizure and non-seizure EEG signals. So the subset Z, O, N, and F, they are combined to form the non-seizure class, and subset S form the seizure class. And this methodology can detect patients which have epilepsy from the normal and seizure-free people. And this EMD method can decompose nonlinear non-stationary signal into set of narrowband AM/FM components or IMFs, then which help us to compute the bandwidth due to AM and FM. These bandwidth features help us to find the contribution due to amplitude modulation and frequency modulation components. So here actually we can see this bandwidth due to amplitude modulation of IMFs for seizure and non-seizure classes. So here you can this bandwidth due to AM, the first four IMFs you can see they are able to separate. They are showing some difference between seizure and non-seizure classes. On the other hand, this fifth IMF to eighth IMF, this bandwidth due to AM, that is actually is not able to show the difference. So these first four IMFs they are actually found suitable for the discrimination purpose, and for the AM case bandwidth due to amplitude modulation, and similarly for bandwidth due to frequency modulation case we can see from this figure that first four IMFs they are able to show the difference, or remaining IMFs 5th to 8th IMFs they are not able to show the difference by using this bandwidth due to frequency modulation parameter. So here actually due to that also can be seen with the help of probability values of the bandwidth features of the IMFs with the test. So this feature bandwidth to AM and bandwidth FM. Here this first four IMFs, their probability value that is coming out to be less than 0.05. So that is statistically significant difference. And the remaining this IMFs 5, 6, 7, 8. They are not statistically significant because their probability values are not less than 0.05. So due to actually there's reason we have selected these bandwidth features of the first four IMFs in order to classify these two classes using machine learning based classifier. As like earlier, this analysis itself was sufficient to classify two classes, but here analysis is not giving better classification performance, so we have to go for machine learning based classifier, or we have to go for project that data features in high dimensional space where we can separate them. So this motivated us to use AM and FM bandwidth features of the IMFs of the first four IMFs as input features in the least square support vector machine classifier in order to obtain more accurate classification. So the least square support vector machine actually it is improved version of the support vector machine, and for two class support vector machine we consider the following decision function, which is expressed by equation 6, fx equal to sine wt gx plus b. Here w is the L-dimensional weight vector, gx is the mapping function, and b is the bias. So based on the sign actually we can take the decision in favor of the two classes, whether it is seizure or non-seizure. So this is actually a block diagram of this model, this proposed system. We have features, then we select some features for the training set, and then based on training set, we actually with the help of kernel function parameters, we perform training of this least square support vector machine classifier, and once you have training, then the testing features for testing set. So that fx equal to sine wt gx plus b. So this gives you sine 1 or minus 1. So based on that actually we can identify the both classes, different classes of the these EG signals based by using this least square support vector machine class. So 1 is for seizure and minus 1 for non-seizure, like that. So in this work, these following kernel functions are used: polynomial kernel, that is given by the equation 7, and radial basis function, which is expressed by equation 8, and Mexican head wavelet kernel function, which is actually defined by the equation 9, and Monolith wavelet kernel function, which is defined by the equation 10. So three classification actually perform measures have been used in this work. Sensitivity, which is the proportion of the epileptic seizures correctly detected by the algorithm, and mathematically it is represented by this expression that is TP upon TP plus Fn into 100%. So TP is true positive, Fn is false negative. Specificity is the proportion of the segments without seizures or non-seizures correctly detected by the algorithm, and mathematically it is given by Tn upon Tn plus Fp. So Tn is true negative and Fp is false positive. Accuracy is the proportion of correctly detected seizures and non-seizures by the algorithm, and which is defined expressed mathematically by TP plus Tn upon TP plus Tn plus Fp plus Fn. So in that way, these three classification performance measures actually have been evaluated, and this table shows the sensitivity, specificity, and accuracy of the IMFs with different kernels of the least square support vector machine classifier for classification between non-seizure and seizure easy signal. So for the following kernel functions, polynomial, RBF, Maxcan, and Morlet, this kernel parameters, this L equal to 5, sigma equal to 0.4, A equals to 1, A equal to 0.6, omega 0 equal to 0.75. They are actually obtained based on a trial and error method. And from that, actually, we determine statistical parameters, sensitivity, specificity, and accuracy. And here in this table, you can see their values, minimum, maximum value of these performance measures. So from this table, it is clear that second IMF actually gives the better classification performance with the help of this Morlet-Wavelet kernel function, which also we validated with the help of this area under ROC curve, receiver operating characteristic curve, and this ROC curve actually the plot of sensitivity versus Berman specificity, and from this plot we compute the area. So if area is coming out to be 1, then it is best classification performance. If area is coming out less than 1, then it shows the poorer performance or degrading performance with respect to that ideal one. So when you see the area computed from the various kernel functions, polynomial, RBF, Maxcan, and Morlet, then Morlet case area under curve is coming out to be 1. So this actually performance measure also validates the higher performance of the Morlet-Wavelet kernel function together with the second IMF for the least square support vector machine classifier. So it's very actually useful result, that is feature space for testing set of the LSSVM classifier with Morlet-Wavelet kernel for second IMF of easy signal. And here actually here you can see the two separate regions for different like seizure and non-seizure easy signals. And this can be used as a tool for diagnosis of the epilepsy. So like for example, rural areas, we can record the EG signal and then we can decompose this using this EMD method, and then we can select second IMF, then we determine AM and FM bandwidth, bandwidth due to AM and bandwidth due to FM, and then we can actually project these features in this dimension, two-dimensional space. And if this bandwidth AM, BFM, bandwidth AM, if it is coming in this region, shaded region, then we call it as like a seizure, otherwise it is non-seizure. So in that way, we can automatically identify the seizure or non-seizure by using such kind of tool, and is one of the important part of the computer and medical diagnosis. And such actually this software such as can be installed in the smartphone, and nicely you can see this display in the smartphone itself, and based on that banding can be given to the patient or to the subject, so that he or she will be careful, and if it is early detection of epilepsy, then he or she can go to the hospital for the treatment. There are various methods in the literature for classification of seizure and non-seizure EEG signals, like Todlas, others 2007, Okak 2008, Liang and others 2010, Ling and others in 2011. They have actually proposed various signal processing and machine learning based methods for this classification of seizure and non-seizure EEG signals. And here you can see these various signal processing and machine learning techniques. They provide the various classification accuracies, and that in the last column of table it can be seen. And the proposed method, which is based on the empirical mode decomposition, bandwidth features, and least square support vector machine classifier, which provides the classification accuracy between 99.5 to 100%. So that our proposed method actually has provided better performance than the other existing methods in the literature, which have studied on the same database. After that, we have proposed the epileptic seizure detection algorithm, and the detection of epileptic seizure, our visual inspection of each signal is very time consuming, and it may be inaccurate, particularly for long data recording. So when a seizure actually occurs, the automated seizure detection method can help in providing immediate required treatment for the epileptic patients. For example, this epileptic patients or someone driving a car, and he or she is going to have epilepsy attack, and this such methods actually can detect this attack in advance, and based on that actually advance detection, this person can stop the car, driving the car, and then this epilepsy drugs or required medicines can be given in order to bypass this attack. So the instantaneous area which we measured from the trace of the window dynamic IMFs of each signals can provide rule-based detection of epileptic seizures. And the EEG dataset, which is publicly available by the University of Freiburg, Germany, has been used in this work. And this dataset actually includes invasive EEG recordings of 21 patients suffering from medically intractable focal epilepsy. So there are two types of EEG signals. One is surface EEG recording, and second are invasive. So surface, they are recorded from the outside of the this by the electrodes, surface electrodes by the skull, and this invasive EEG signals, they are recorded from the inside of the brain. So you need to have some surgery kind of thing. So when you have generalized epilepsy, then we go for surface EEG signals. They are recorded outside of the brain, and in case of focal epilepsy, around 80% actually the cases. This is not this is drug resistance epilepsy, so these medicines doesn't work. So you have to go for surgery, or you have to go for this surgery. So in order to have that, you have to identify the focal EEG signal, so that you need to record signals for high SNR, signal to noise ratio is very high. So we record such signals from the inside of the brain, and where machine learning and signal processing techniques find very actually a useful application in order to precisely detect these signals to perform the diagnosis of focal epilepsy. The EEG data actually is required using digital video system with 128 channels and sampling at 256 Hz and 16 bits analog data converter. And in this study, 3 intra-source records of 9 patients with focal epilepsy originated in the temporal region have been selected. So this actually gives total 90 segments each channel, and 51 of them without epileptic seizures, and 39 segments denoted as having only one epileptic seizure. So after that, this is actually very interesting results. Here see signal, and the signal actually has epileptic seizure in the middle, and that is actually not easy to identify. So when you decompose this signal in terms of IMF, IMF1, IMF2, IMF3, and here you can see second and third IMF, it is boosted up. It shows the actually there is this improved activity. So like signal strength is more clear after decomposition. It will be more clear when even like you apply this tenderness area detection. So this is the signal which has actually this epileptic seizure onset in the middle, and this is the computed instantaneous area of the first IMF, second IMF, third IMF. You can see this first IMF, second IMF, third IMF, these three all areas. There this shows the boost up when there is epilepsy attack. On the other hand, it is not clear from the raw data, and this dashed line in the beginning and ending, this shows the region of the seizure which is detected by the neurologist, and our this circles actually that actually proposed by our method, they detected by our proposed method, and you can see this beginning and end of this seizure, onset and offset, that actually is coming in the range of this is the range of the reference which is provided by the neurologist. So our proposed method actually can be used in an alternate of the neurologist for the diagnosis of the epilepsy, or for the detection of epileptic seizure at early stage. So the epileptic seizure detection based on the instantaneous area of IMFs has been performed by using following decision rules. The first decision rules requires computation of the threshold of the instantaneous area of IMFs of each signals for all channels. And the threshold of the mth IMF is computed by equation 11. And this is actually this this expression has been computed by the either empirical in nature based on this data, and for other data we can come up with the this similar kind of threshold for other data. Second decision rules requires the identification of those seizure activities which are available in at least 2 of the 3 instructions area of IMFs of each channel. And finally, the third rule requires making an inter-channel decision based on the identification of those seizure activities which are available in at least 2 of the 3 channels, where presence of seizure activity in each channel is decided by the rule 2. So in that way, based on the majority, actually we can take decision for the for the seizure detection based on the, like, out of 3 channels, if 2 channels are capable of seizure, then we say this is seizure. If 2 channels are seizure free, then we say it is seizure. So based on the majority, we take the decision, so it is more reliable. So now this table shows the performance evaluation parameters. So for the different patient segments, this is true positive, number 2 negative, false positive, false negative, and sensitivity, specificity. Already mathematical expressions have been provided in the previous slides for these 2 performance measures, and the remaining positive predictive value, negative predictive value, error detection, their expressions can be seen in the bottom of the slide. So here positive predictive value is a mathematical expression, and error detection, ERD, is a mathematical expression. Negative predictive value, this is a mathematical expression, and it should be it can be seen actually from this table that sensitivity, specificity, PPV, NPV, they are actually, they should be high for a good method for epilepsy detection, and ERD is expected to be less, and the proposed method, from the results you can see the sensitivity, specificity, PPV and NPV is coming to be high, and ERD parameters coming to be less. Then we have compared our method with other existing methods in the literature. So this Orozco others 2009, they use energy of IMFs of these signals, and they got various the parameters, sensitivity, specificity, PPV, NPV, ERD. And Correa others 2009, they use energy of EG signals, and they got various sensitivity, specificity, PPV, NPV, and ERD. And proposed method that is based on the instantaneous area measure of analytic IMFs of EG signals, that gives you better accuracy, sensitivity, better specificity, better positive predictive, better negative predictive. So these are higher values than the other existing methods in the literature. Similarly, ERD is coming out to be lesser than the other existing methods in the literature. So this means that our proposed method has provided better performance with respect to the other existing methods in the literature which have been studied in the same database. After that, actually, this time frequency image based features for classification of sleep stages have been actually proposed, and this in this actually part we have used this time frequency distribution in the form of image. So time frequency analysis is also actually one kind of transform of the signal in time frequency domain, which is suitable for analysis of non-state signal. And the time frequency distribution, energy of the distribution changes with respect to time and frequency. So this energy is positive quantity, so we can convert it this in the form of image intensity, and we can actually get time frequency image from the time frequency distribution, which is very useful for signal analysis. And we have studied for the classification of sleep stages. And this is actually very interesting approach these days to use this advanced machine learning techniques like CNN, convolutional neural network, deep learning, where this image actually itself can be used as a signal, as an input. So in these advanced machine learning techniques, our data, our signals should be in the form of image. And this time frequency distribution or based time frequency image provides such a platform where this time signal can be converted into time frequency image. And like a speech, for example, ECG signal, and normal abnormal classes, you just convert a speech signal with the help of time frequency image. You can convert EG signal with the help of time frequency image. So by doing this, and nicely you can separate these normal and abnormal classes of the actually signals using this time frequency image. So standard method of sleep stage recording and manually sleep staging is based on the criteria proposed by RNK standard. And according to RNK standard, the sleep actually consists of 6 different vigilance stages, namely awake, non-rapid eye movement stage 1, as non-rapid eye movement stage 2, non-rapid eye movement 3, non-rapid eye movement stage 4, and rapid eye movement. So actually this total 6 stages are there, and this rapid eye movement, that is actually very important stage, and that is responsive for the dreams. So sometimes rural areas, people interpret actual dreams in very nice manner. They take them seriously, and sometimes if you have seen the dream in the villages, and if you say your families, neighbors that you have seen the dream, they will ask you what time you have seen the dream. Suppose you have seen, you will tell you have seen the night 12 o'clock, then they will not take seriously. But if you say you have seen the dream in the morning around 4 o'clock or 3 or 5 o'clock, then they will take it seriously. And then actually, so that in India, this rapid eye movement, that is like the morning time. And based on the actually based on the whatever you see in the dreams, the village people interpret. And like if you have seen the elephant in the dreams, they will interpret something. And if you have seen the gold, then they will interpret something. And for example, if some girl has seen the bangles, then village people will interpret that like she is going to get married this year. So this is like they start celebrating, they start preparation for that. So actually the old time also, Ramayana time, Treta Yuga, Mandodari actually observed in the dream that her husband Ravan is going to die, and she also informed the same thing to Ravan also. So this actually these dreams also have some kind of information, and that is also actually area of research these days. People want to understand the dreams with the help of signal processing machine learning techniques. And this is actually this rapid eye movement that is responsible for the dreams. And this alcoholic people, they take the alcoholic people, they don't cover rapid eye movement cycle. So they don't actually include this sixth stage rapid eye. They have only 5 stages of the sleep. They don't have 6. So indirectly, they accumulate the depression, they accumulate the sleep-related disorders, and the alcoholic people cannot see the dreams. So that is actually, so alcoholic means it is like accumulation of the sleep state related disorders, depression, and that is not good for health. Recently, another method of sleep staging developed by the American Academy of Sleep Medicine, ASM, which actually combines sleep stages as 3 as score of RNK standard into single stage known as slow wave sleep or deep sleep. So the manual method of classification of sleep stages is a very time consuming task and prone to inter and intra scoring variability. And moreover, the manual sleep scoring is performed by trained professionals and clinicians, and the reliability and agreement of manual sleep scoring may be unsatisfactory because of subjective judgment and possible human error. So due to these reasons, actually there is a lot of interest in the literature to use the signal processing and machine learning techniques for classification of sleep stages, which are multi-class in nature. So now we see the proposed methodology. We have EEG signals of sleep stages S0, S1, S2, S3, S4, S5, 6 stages. Then we obtain time frequency representation using pseudo-Wigner-Village distribution method. Then we perform this segmentation of time frequency image of each signals based on the frequency bands of rhythms. And then we calculate features based on the histogram of sub-images of the EEG signal. Then multi-class G-square support vector machine has been employed for the classification of these 6 stages, 6 sleep stages: awake, S1, S2, S3, S4, and rapid eye movement. For the study purpose, we have actually used EEG dataset, which is publicly available online by Physionet website. And this recording actually has been obtained for 8 males and females whose age vary from 21 to 35 years and without any medication. And the recording actually includes horizontal FPGA signals, is sampled at 100 Hz. So according to RNK standard, this EEG data actually has been divided into 30 seconds epochs. So in that way, total 4,700 epochs are there in different classes, and this has been arranged according to RNK standard, and this the night 12 o'clock to 5 o'clock morning, this 5 hours time is sufficient to include all actually sleep stages, in order to have all sleep stages. So now we will see some. This is the equation 11, shows the mathematical expression for smooth pseudo-Vignavali distribution, and this is the one example of computed time frequency distribution using this smooth pseudo-Vignavali distribution. And here this for the EEG signal corresponding to rapid eye movement and cycle. And then distribution is converted to image. So this is the time gray image representation of time frequency image using a smooth pseudo-Vignavali distribution of REM sleep stage of EEG signal. This actually gray and whiny sub-images represent time frequency corresponding to frequency bands of delta, theta, alpha, beta, and gamma rhythms. And for the gray, you can see the left side, and for the binary, this is right side. So the segmented rhythms can be seen in time frequency image. Then we have obtained the histogram of gray and whiny sub-images of time frequency image corresponding to frequency bands of delta rhythm, theta rhythm, alpha rhythm, beta rhythm, and gamma rhythm. Then we have proposed these features based on the histogram of sub-images of the EEG signal. The maximum count of pixel intensity, the histogram of gray sub-images shown by the equation 12. The spread in the histogram of gray sub-images shown by the equation 13. And the aspect ratio in the histogram of binary sub-images is defined by the equation 14. So these actually features have been computed, and here, like earlier, we have used least square support vector machine for classification of two-class classification problem. Two-class classification. Here, actually, this is multiple stages of sleep data. That is actually multi-class classification problem. So, for example, RNK standard is 6-class classification problem. For American Academy of Sleep Medicine, is 5-class classification problem. So, the decision function of multi-class least square support vector machine defined by the equation 15. So, here you can see this KK x, x is the kernel functions. So, now we have multiple kernels here for multiple classes. And in this work, following kernel functions have been used: radial basis function RBF, which is defined by the equation 16, and Mexican head wavelet kernel function defined by the equation 17, and Morlet wavelet kernel function defined by the equation 18. And now this table shows the results without segmentation of time frequency image and with segmentation of time frequency image. And here you can see when we are not doing segmentation of time frequency image, then these are the kernel functions and parameters based on a trial and error method, which has given best performance. So here you can see, for example, Morlet kernel function without segmentation of time frequency image, it gives you 79.99% classification accuracy. And when you perform segmentation of time frequency image, then it can give you 92.93% classification accuracy. So in that way, actually, it is better performance. So by segmentation, there is huge improvement in the classification. So this also motivated us to actually use the segmentation of time frequency image before performing the classification. This table shows the confusion matrix for the classification accuracy of the sleep stage of EEG signals for Morlet wavelet kernel with window size of 64 samples. And then actually we have compared our method with other existing methods which are studied on RNK standard. So Doran-Sonke in 2007 is a 50 based feature Markov model, and they got total accuracy 61.08%. And Borare 2010 is hybrid features and cluster based classification principal component analysis. We got 69.98% classification accuracy. And proposed method, which is time frequency based features and multi-class square support vector machine classifier, it provided 88.47% classification, which is higher than the other existing methods in the literature. And American Academy of Sleep Medicine, relatively less work has been done. So there was one work was available, that is Sue and 2013. They use energy-based features and Lehman neural classifier. and they got 87.20% classification accuracy. And our proposed method, which is based on time frequency image based features and multi-class each classable vector machine classifier, provide 92.93% classification accuracy, which is higher than the other existing methods in the literature. So after that, in the end, in the last actually, we have developed multivariate transform based features for human emotion classification, and this is also actually very important part, because emotion is very important part of human. And EEG signals contain valuable information related to different emotions, which help us to understand physiology and psychology of the human brain. And there are various methods for the emotion detection, like speech based method, speech processing based method, and face recognition based methods. So these methods actually can be manipulated, like the face can be modified, speech can be modified, so that they are not more reliable. But EEG signal based methods, they are actually EEG signals are recorded from the brain, so they it is difficult to manipulate them. So this EEG signal based emotion detection is more reliable. And also emotion classification using EEG signals can help us to develop and improve brain computer interface BCA system. And this BCA system can be used for assisting the physically disabled and impaired people to interact with the real world. So here actually, like for example, newborn baby, they are not able to speak. So we can record their signals, and for the example, they are not feeling well. Then we can provide the treatment, and after treatment we can record signals. So we can see the changes in the actually signals, and based on that we can understand whether this treatment is showing effect or not. So in that way actually we can interact with disabled and impaired people, or those who are not able to speak, to interact with the real world by doing this BCI based on the emotions. So this is the actually block diagram of proposed method. We have experiment setup, pre-processing, multi-wavelet transform, then Euclid distance based features from the three-dimensional phase space reconstruction. And once you have these features, then you apply input as a multi-class support vector machine classifier, which automatically classify happy, neutral, sadness, and fear emotions. And these EEG signals have been collected from 8 healthy subjects, 4 males and 4 females, whose age vary from 20 to 35 years, during audio video stimulus. And the subjects were undergraduate students or employees from IIT Indore. In 16-channel EEG module, BioPAC system in compliance to the International 10-20 system was used for the recording of EEG signals, and the sampling rate was 1000 Hz of the EEG signal with bipolar montage for this study. So this study has examined 4 emotional states, which include happy, neutral, sadness, and fear. And in this experiment, 3 audio video stimulus, 5 trials of each emotion, 8 subjects with F3, F4 channel of signals have been used. And total we have 480 EEG signals, each and 2 second duration. So this shows the actually electrode cap of this location of the electrodes for the recording of EEG signal for this emotional study of emotion. And this shows the arousal and balance diagram for the location of these emotions in this diagram. And this is actually block diagram of complete methodology for human emotion detection. So you have this person is watching video, and based on that is this emotion is introduced, and then we record EEG signal, and then we perform pre-processing in order to reduce noise or unwanted frequency components. Then we apply non-state signal decomposition, and then based on these components we extract features. Then we perform classification using multi-class G-square support vector machine classifier. This multi-wavelet transform is actually uses multi-wavelet as a basis function. So multi-wavelet is the extension of idea of scalar wavelet, where multiple scaling functions are associated, multiple wavelets are used instead of single one. The multi-wavelet offers the advantages like simultaneously orthogonality, so it supports symmetry and second order approximation. So 3 commonly used multi-wavelets are employed in our work: GHM, CL, and SA4. And concept of phase space is very important tool for characterization of high-dimensional dynamic systems. So in order to extract the nonlinear dynamics of the sub-signals which we obtain from multi-wavelet transform, we have used the phase space reconstruction plot, and mathematically phase space reconstruction of the subband signals obtained from multi-wavelet transform expressed mathematically by the following formula. And this is actually one example of third level decomposition. Third level decomposition, then you will have three details, one approximation. So four subbands will be there, and you can see this phase space representation of these four subbands, and it shows the variability, and that is linked with the emotions. So that actually can be computed with the help of this following proposed features: mean of equilibrium distance and standard deviation of equilibrium distance. Can be come to equation 19 and 20. And now we'll see some experimental results. So the proposed method GHM, CL, SO4 multivariates have been used for the signal decomposition, and third level decomposition has been actually performed, so that we have four subband signals. Then we have computed phase space representation of these subband signals. Then we have determined the features, mean of distance and variance equidistance, standard deviation. And the mean and standard deviation of Euclid distance of 3D PSR is summarized the computation this complexity of decomposed subband signals, which is linked with the different emotional states of the human brain. And finally, these features have been used as an input to multi-class square support vector machine classifier with RBF kernel, Mexican head, and Morley Wavelet kernel functions. So this table shows the actually this classification accuracy with different kernels of the multi-class square support vector machine, and with different multi-wavlets. So GHM, SFO, CL, and different kernels RBF, Mexican, Morley, and these parameters are computed based on a trial and error method. And these are the obtained actually accuracies for happy, neutral, and sad and fear emotions. And so they are total accuracy. And here you can see in CL multi-wavelet together with actually the Morley wavelet kernel function, it gives you 91.04% accuracy. This is higher than the other multi-wavelets and other kernel functions. So this table shows the confusion matrix of Morley wavelet kernel function of the multi-class square support vector machine classifier for classification emotions using each signal with CL multi-wavelet. And then we have compared our proposed method with other existing methods in the literature, like Lina 2010 is music of 30 seconds with 24 channels. STFT method was used, and KNN and LD classifiers got 82.29% classification accuracy for the same four classes. And Wang 2010 used video of 4 seconds with 62 channels and minimum redundancy, maximum relevance with support vector machine classifier for 66.5% classification accuracy with the same four classes. And proposed method has used audio video of 2 seconds and with using multi-wavelet transform and multi-class square support vector machine classifier is provided 91.04% classification accuracy for the four classes. So this is the conclusion of this entire talk. The area which we have measured from the trace of the analytic IMFs have circular form in the complex plane and can be used as a feature in order to discriminate normal EEG signal from the epileptic EEG signals. Bandwidth parameters, bandwidth to AM and bandwidth to FM of the IMFs of EEG signal can be used as a feature in order to classify seizure and non-seizure EEG signals. And the classification results and values of statistical parameters shows that the Morley wavelet kernel function of multi-least square support vector machine classifier can provide higher classification accuracy for the classification of seizure and non-seizure signals. And we have proposed patient-specific system for detection of epileptic seizures from EEG signals. And the instantaneous area which we have obtained using this moving window of smallest size on analytic IMFs can provide good detection performance for rule-based detection of epileptic seizures using EEG signals. And time frequency image representation makes possible to compute histogram-based features of each sub-image of EEG signals corresponding to the different frequency bands or EEG signal rhythms. And the histogram-based features are very useful for automated sleep stage classification from EEG signals. And the classification results have shown results show that the Morley wavelet kernel function of multi-class square support vector machine classifier can provide a 92.93% classification accuracy for sleep stage classification using EEG signals. And the mean standard deviation of Euclidean distances based on the 3D phase space reconstruction of subsignals can be useful to measure the emotional changes of the brain. And the classification results show that the Morley wavelet kernel function of multi-class square support vector machine classifier with CL multivariate can provide 91.04% accuracy for the classification of emotions from single channel EEG signals. Thank you very much. Any questions, please?
Ask the question.
Any questions, please?
Dear participants, any queries? It's open to you now. Okay, sir. No questions. Sir, it was very nice session we had. So actually, the session was about EEG signal classification, different types of EEG signals and different methods of classification using supervised, unsupervised classifiers, and how to represent the result. So these things were analyzed in a very well way. So thank you very much, sir. On behalf of Department of Electronics and Communication Engineering, SR University, I express my deepest gratitude. Thank you so much, sir. We are very happy to hear you has a eminent personality on this FDP.
Thank you
For
very
any
much.
participant, those who want to have any queries, you can ask anytime also. So we'll end up the session now. Actually, sir, one thing, we are proposing one book from CRC on EEG signal, BCI. It is already accepted by CRC. So from your side, please give some chapters for the book. So
Yes.
personally, I will be sending you the invitation for the proposal. Please one or two chapters from your end, sir.
We will do that. It is
Thank
all.
you. Thank you, Professor.
Thank you.
Thank you, sir. So participants, tomorrow will meet.